Good morning, everyone. Let's give people some time to join. I'll just give it another minute or two for people to join. Okay, let's get started. Looks like we have about half half the people joining, but if they're not joining by now. All right, welcome back everybody to System Software. I hope everybody had a good week and had an opportunity to take a look at that toy compiler that we compiled together last week. I know that went a little bit quickly, but you still have another week to type that up and get it running on your own. So recall, here's the due date for that toy compiler. And remember, you don't have to reinvent the algorithms. It's really just a way to exercise using Makefiles and Git to build, run, test, and record your code. Today's lecture is going to be on compilers. Turns out that some of the more tedious parts of writing the compiler, the lexer and the parser, can be automated. And so today we'll go over the toy compiler again and then see what it looks like when we use some of these compiler tools. So here's the table of contents for today's lecture. And remember that the lecture notes, which have everything from the slides, will be linked from these lectures. So if you click on this link here, you'll get all the lecture notes. And then we'll go over SimpleC, the language that we'll be implementing as a semester-long project for this class. So I guess the first thing to do is to look again. I know we've looked at this many, many times. To look again at from a functional point of view, look again at what it looks like to build a compiler. From a very high-level point of view, the compiler is just another program, in our case in this class, written in C. We pass it to our compiler, which may or may not be the same compiler that we're writing. And this produces an executable. And hopefully everybody remembers this. What is the input to the compiler program? So say we're writing a C compiler. What's the input to the compiler program? The language code, exactly, yeah. So in this case, this would be source code in C, for instance. And what is the output of a compiler? Exactly, machine code or object code, code in the target language. There's many ways to say this, but so the compiler is kind of unique among programs in that rather than taking, say, numeric data or strings and producing some numeric output or displaying a graphical interface to you, it's unique in that it takes in programs and writes out programs. It's almost like a program generator. And that's because these high-level languages that are more useful for humans to write, like C, you may think it's funny to think that C is more useful for humans, but compare it to writing in assembly. Writing in C, which is a little bit more natural for humans, but machines don't actually process those kinds of languages. They're using ASCII conventions in order to display text to us. In assembly and then in the machine, you have to run one instruction at a time. You have to reason about all of the RAM at once as one random access chunk of contiguous memory. And so the compiler takes this completely invented language that no machine actually processes and does a translation to machine code, to the language that the machine actually processes, the opcodes and the conventions that the machine developer, the architect, designed for that processor. And last week, we wrote a compiler for this toy language. And we separated it into the several phases of compilation. Does anybody remember what some of these phases of compilation were from last week? Optimization is one. Linking. Well, linking is kind of separate from compilation. But optimization was one. What else did we have? Semantic analysis, good. Type checking. Good. Lexer, parsing, code generation. And those are exactly the three things that we implemented for our toy compiler. Modern compilers have more phases like optimization and semantic analysis or type checking. And recall that the way we used separate compilation as organized by a Makefile we took these three programs, these three C files, and compiled each of them individually, linked them using GCC. So this was actually using GCC to do this. And we linked it into a program called Toy. And this took in our, what am I doing? And this took in our toy language and produced Intel assembly. Which for GCC, .s is the convention for assembly text files. And if you remember, these parts of the compiler, well, maybe all parts of the compiler were fairly tedious. But the Lexer and the parser, in particular, have been studied for several decades, how to make these more systematic. And it turns out that there are some nice computational theories that we can use, some new models of computation that we can use to make this process of writing Lexers and parsers a lot easier to do. So let me, didn't realize I couldn't move text for some reason. So it turns out that we can actually automate the process of generating the Lexer and generating the parser using two special tools called Flex and Bison. And we'll go into introducing these tools today. And so, and these are called compilers, just to make compilation even more confusing. Because these tools themselves are like compilers. They take in some specification language. It's not necessarily a programming language, but some specification language, and automatically generate C code. So now we have multiple levels of compilation going on here, where we have different phases of the compiler being generated using compilers, parser generators, or Lexer generators. And then that C code is being used to define the compiler. it's being compiled into code, and it's being compiled into a compiler, and that compiler takes some other source language and produces a target language. So it becomes a little bit mind warping at this point because we're compiling compilers themselves. These are not the header files. We'll look into what these files actually look like, but these tools, Flex and Bison, these will actually generate C code. They'll generate C code, and that C code represents one phase of our compiler. So we're going to take the lexer that we wrote last week, and instead of handwriting it and having to worry about all the file I/O and working through each character at a time, we're just going to specify. Sorry, my handwriting is very bad, which is why I should be typing this. Keep doing that. Okay, questions on the architecture of our toy compiler. Does anyone have questions about the toy compiler code from last week? So let me bring that up again. So just a quick review of the code. We had several source files here. I should use the not modified version of this. We had each of our three phases separated into 3 C compilation units. Each one of them defined a particular interface for the next phase to use. So the lexer exported this lex function, which was used by the parser. This is extremely small to look at. Let me give you a better view of this. So our lexer exported the parse function, and then our code generator, which produced an AST, and our code generator walked over this AST to produce machine code. So I know you guys have another week to actually write up this toy compiler, but what questions, if any, do you have on the toy compiler from last week, or is it totally clear the way this compiler works? Okay, so the question about how the parser is working, someone says it's clear to them. Coding helped to understand. That's fantastic. Yeah, this is why I wanted you guys to do this exercise. Just, yeah, I mean, at least for me, sort of getting my hands dirty helps me understand a problem much more deeply than trying to just sort of read about it or think about it conceptually. And one of the main things I wanted to get across is any compiler, even if sophisticated compilers aren't literally using printf, one of the main parts to understand about what a compiler does is that it's generating code. And so there's when you went to actually handwrite this, and when you go to write this yourself, if you haven't done it yet, our toy compiler is literally just printing out assembly code. It's literally just printing the text of the assembly. And that's kind of the core of what compilers do. Compilers are code generation technology. They're automating the process of writing out code. And when you get to actually writing this codegen.c, you'll see that there are print statements that are just literally printing out assembly code. And in our case, we can kind of make this simple by having an assembly instruction template where we use the printf formatting to do this, but the value that's being moved into the B register is parameterized by the input language. The input language had some number in ASCII code that we converted into a machine representation, and then we just print out then we just like literally print out assembly code that has that number in it. And yeah, so all the kind of rigmarole that we do to get to this point of generating code is really all about making sure that we can print out equivalent assembly code. Somebody asked what the money sign means. This money sign in ATT Intel syntax is indicating an immediate value. If we look at the output here, you'll see that this is the code that gets generated. We have money sign 5, and that just says take the machine representation of the integer 5 and move it into the register B, EBX in this case. So the different versions of B, so EBX or RBX, these are just the different bit widths. And I can never remember which are which. So I think EBX is 32 and RBX is 64. But correct me if I'm wrong. I'm not an assembly programmer. But once we get to the third phase of this class, we'll look in more detail about the Intel ISA specification, the instruction set architecture. Okay, we had a question about how the parser is working. And we'll look in a lot more theoretical detail in a couple of weeks how parsing works from a kind of formal computational point of view. But intuitively, if you went to lab last week and saw Josh talk about syntax and grammars, the parser is effectively walking over the syntax tree of the input language. Recall that human languages and languages in general, particularly human, which is probably, there might be a biological basis in humans for this, but the kind of computational understanding of languages is that they have this hierarchical syntax. Recall this famous notion from Noam Chomsky about the separation of the syntax versus semantics, that we can, and this is not something, the grammar is not something that Chomsky came up with. For thousands of years, scholars have known about this kind of hierarchical syntax that languages have. In fact, one of the earliest grammars developed was for Sanskrit, the ancient, now dead language that was one of the oldest that we know about in the Indo-European languages. One of the scholars had written a grammar for Sanskrit. And a grammar provides this hierarchical relationship between the different parts of utterances in the language. So at the very top, you have the kind of, and now that you guys have seen CS1 and CS2 and seen trees and tree walking algorithms, you see that trees are this very natural representation of this hierarchy, this natural data structure that we can use for this hierarchy. And so we can look at language as kind of having this hidden hierarchy of symbols behind the scenes. So even though the utterance is colorants, green ideas, sleep furiously, that's what when we utter the words, those are the only words that we say, but we can kind of infer that there's this structure going on behind the scenes about the language. And Chomsky's rationale for this was that even a meaningless sentence like colorless green ideas sleep furiously has some sense of correctness to us when we see this, whereas something that is not syntactically correct does not. And syntax essentially provides constraints on the legal orderings of words, on the sensible orderings of words that is independent of the actual meaning of the language. So just to answer one quick question, so this is kind of separating syntax and semantics as well. So somebody asked, so you don't really even need to know assembly to write compilers. This is kind of more or less true. You don't necessarily have to be an expert on assembly. If you want to write compilers that work really well, you should, and are fast, you should definitely understand assembly in detail and how the architecture works. But this is kind of a difference between being able to look at a reference manual to write a language versus being able to sort of naturally, off the cuff, be able to write code. So for compiler writing, we just need to know enough about the specification of assembly in order to generate code. Because remember, we're not writing assembly. We're writing code that writes assembly for us. And this also kind of gets to the heart at compilers and these kind of theoretical computational notions of language, is that you can kind of separate this, this is what's describing in this Wikipedia article, that you can kind of separate out these notions of syntax, which are really just constraints on the symbols that we use to represent whatever it is that we want to mean in the language, and the meaning itself. And in the compiler, we can see this in the separation between the front end, lexing and parsing, and the back end, code generation. In the front end, remember that when we wrote our compiler by hand, the representation of the language uses ASCII code. And ASCII code, the actual numeric conventions for ASCII code are different from machine integers. When we want to represent a machine integer, which is the classic 2's complement for negative, or the regular binary representation that we all learn about in architecture, that's not the representation that ASCII uses. ASCII uses a different encoding for that. And in the front end, we are processing that without, completely independent of the actual machine representation or the actual semantics of that number. It's just a symbol that we define as representing that number. And the way so at least for compilers, the way we define the meaning of those symbols is to translate it into another language representation, in our case, assembly. So this is kind of a tricky thing to wrap our heads around. There's some kind of interesting philosophy around this, the symbol versus the thing it represents, or the moon versus the finger pointing at the moon, these classic Chuan Buddhism koan or whatever it is. And we see this in full force in the compiler, where the input language has no meaning without the compiler interpreting that meaning. And in the compiler's case, interpreting that meaning by defining it in terms of another language. So there are lots of formal ways in computer science to define semantics of programming languages. But for the compiler point of view, we define the meaning of the input language in terms of another language. And it's almost like, passing the buck or turtles all the way down. But for the compiler writer, the hardware is the interpreter of the assembly language. And so we just rely on that sort of physical manifestation of the language in order to define our input language. So maybe this is getting a little bit conceptual. And actually we'll see once we start looking at the Parser Generator, the compiler work, that this distinction between syntax and semantics is very clear. And the Parser Generator actually provides us a mechanism for defining the semantics of our language. Okay, so this is a big tangent off of the main question, which was, how does this parser work? And until we get into the kind of theory of it, basically you can think of the parser as walking the syntax tree, as basically a set of recursive functions that will be able to recursively traverse any program, any input program, traverse its particular syntax tree. So this is almost like a definition of all possible syntax trees in the input language. And when you actually run one particular input language, the parser is traversing that input language's syntax tree or grammar tree. Does that kind of make sense for the person who asked about how the parser works? So if the top of every syntax tree is a statement list for any input program, then we write a function that says, well, here's the root of the node, so always parse a statement list. And inside of it, it's parsing the two symbols that every input language has. The two symbols are a nested statement, or a statement followed by a statement list. So it's almost like defining the grammar as a set of recursive functions. And so it parses the statement list, and parses the statement, and then parses the statement list. And then the recursive function that parses the statement calls the thing that every input language has, which is an expression underneath of it. And then that expression, now at this point, there are no more grammar nodes to look at. So this parser just gets the actual tokens from the input language. And we'll see when we get into the parsing theory that there's this distinction, just like we saw in this grammar hierarchy, there's this distinction between the terminals or tokens or actual utterances in red here, and the kind of symbols that are implicit behind the scenes, the symbols that themselves define the grammar structure. And one of, I guess, sort of Chomsky's innovation here was that these symbols, even though they are not spoken, these symbols are actually physically manifested in the brain, physically, to kind of encode and walk and process this input language. So we'll see in whether that's true or not. This is sort of a controversial idea, even still in psychology. But in computing, we can use this notion that these are physical symbols to define our language and to define a syntax tree. So our syntax tree, there's a data structure that not only has the actual input language, but has physical symbols for each of these parts of the input language, each of these constructs in the input language. And we'll see more about that theory. For me, I think this area is very interesting for me. Actually, some of my research is in parsing. It's not an area that gets a lot of movement because it's considered largely solved in compilers. But there are some, so to brag a little bit, I made a small kind of contribution to an unsolved problem in parsing, particularly for C, several years ago. And one of the hardest things was, when I gave the talk at the conference in this, they said I solved one of the hardest problems, which is getting a parsing paper in this conference, because people don't really, there's not a whole lot of movement in parsing. But I find this area really interesting, and so I'm willing to go through the tedium and difficulty of I had to flex on this. But very very small accolades for that. It's a very niche area. But yeah, so I really enjoy this stuff. We'll see some of the theory in a couple of weeks about how parsers actually work theoretically. Okay, other questions on the toy compiler? So somebody asked a kind of build question about what happens if the program keeps complaining about undefined reference. So when you say program, do you mean when you build or when you run? When you use the make command. So when you build, it just means your header files, so let's see. Yeah, so it means that wherever, and actually we'll review this today, the way makefiles and separate compilation work. Because I think this is in the, when I said that I think great compilers have these three technical areas of knowledge: the language, the programming tools, and computational theory. this is understanding Makefiles and the compiler. This is part of understanding your programming environment. So this is not really something that is super academic or scholarly. It's often not taught in school, but it's really important to know about if you actually want stuff to build and run. And so we'll cover this a little bit more today, how this works. But in short, the reason that your make is, oh yeah, great programmer, sorry. Yeah, so the compiler is like an automated programmer. Maybe I'm confusing myself. Okay, so somebody asking about undefined references, not the compiler is complaining about that. So that's what these header files do. So if you, well, actually, let me see if, I think this is the next part of my talk, of my slides anyway. So let me, what did I have next? Well, okay, I'll get to that a little later, but the basic problem is that the compiler is just unaware of those functions. So it's either the compiler or the linker that is just unaware of either the declaration of those or the definition of those. But let's look, and let's wait till separate compilation in a little bit to see in detail how that works. But basically, you either haven't written the definition of that, and then when you get to linking, the linker can't find that definition of the function. So maybe you just didn't finish writing the code. Or your compiler is complaining that it doesn't know the type of that function. So somebody asked, what should you turn in? Turn in all of the code necessary to build and run the compiler. So basically everything listed in, so if we go back to lecture 3 here, everything listed under resources here. So here is the list of files. Well, so you don't necessarily have to turn in the example stuff, but everything that is C code and the Makefile, turn that in. So basically you want to have a complete program. You want to have a complete program that you've been able to build, run, test, and version control. And if you can do that, that's fine. I mean, these are, you know, you can include these. I included these in my code just to have example code in there. But strictly speaking, and so another point that I kind of glossed over when I talked about version control is, by convention, generated files do not need to go into version control. So this is really a convention. This is not a hard and fast rule. There may be good reasons to have generated files. Say you don't want to have the user have to have those tools on hand. But almost certainly binary files, like object files, are usually not included in version control because it's source version control. It's to maintain the source code. And the idea is that you have all the automation and instructions available, ready to be able to generate that code for you. There's also practical reasons for this, that if you want to clone your version control, it's nice to have it very small and fast to clone. And if you keep all the binary files in there, it's going to be really large. But yeah, typically a well-defined version repository will tell you, here's the dependencies, here's the versions of each of the tools that you need to install. And ideally, you can use some package manager to go out and get all those right versions of the system tools you need, and then just run one command, whether it's make or a script, and that will just automatically do the build for you, and then you'll have your program ready to go. And so source version control repositories rarely need the compiled or generated code, with exceptions, of course. So no need to submit .o files. And in fact, so a little separate tangent here. Git and other version control tools have a special hidden file called Git Ignore, and so that when you say Git status, you don't always get Git telling you that there are these untracked files. Git Ignore will allow you to tell Git that these files are never to, I never want to commit these files. These are just generated files. or files that I don't want to be part of the repository. And that way you have a nice, clean repository that when I say git status, it just tells me nothing to commit, working tree clean. So even though I have all of these .o files in my repository, so so for various reasons I put these in multiple locations, but I have this Git Ignore file that says, well, I never want to have .o files in my repository, so just always ignore those. These are backup files from my editor, Emacs, so I never want to have those committed as well. And so even if I delete these .o files, when I say git status, git status on my current directory, it tells me that there's nothing to commit. And even when I run my make and it builds all of these .o files and builds the toy compiler, because this is not source code and I don't want this to be controlled under source code repository version control, then I just put that in Git Ignore. And I made some changes here that I'm gonna push because I forgot to do this. Yeah, I may release these toy compilers at some point in the future. I made a private repository to hold these in, these two versions that I have of the compiler. So somebody mentioned typing speed. You know, if so this is kind of part of the impatience virtue of programmers. You know, I just want things, all the tedious stuff to be done fast. And if you're doing debugging, it actually is really useful if, you know, without going into great detail in debugging, it's really useful to be able to like run and compile your code quickly. So part of the reason that I do things on the command line is that I can quickly switch between compiling and running and editing as fast as possible, just so I can do debugging faster. I mean, it's a linear speed up. It's not a theoretical like big O speed up, but it's a linear speed up, and that's still a real speed up. It makes things faster. If you're taking a minute between compiling and running, then you know if you can have that, then you're going to have the amount of time, part of the amount of time that you take in compiling. So somebody asked about how I made the Makefile. So I will always provide the Makefile in the future. I think I had you hand copy the Makefile for this. I can't remember if I provided it with you or not. But from this point on for the project, I'm just going to give you the Makefile. Makefiles are kind of a massive pain. They're very archaic, esoteric. They use lots of symbols. You have to use tab instead of space. Otherwise, you know, I think some students had trouble with this where the make was complaining. They're super esoteric. I always have to look up, even if I've written many Makefiles, I still have to look up a reference just to remember how to do stuff in Makefiles, which to me is a sign that they're, you know, not intuitive to use. Yeah, so I give you the Makefile for, I just give you the text. It looks like I just give you the text of the Makefile for the toy compiler, and I'll definitely do it for the SimpleC compiler. But you will have to edit your Makefile during the SimpleC project, but I'll give you the kind of starter Makefile. Okay, other questions on the toy compiler, other issues? So somebody asked, how should you go about debugging Seg faults? This is a good question. So to kind of review what I think I talked about in lecture 1. So this is really a nice kind of schema for doing any kind of debugging. So if you've already narrowed down or done test case minimization is the kind of technical term for this, and you've sort of identified the general area where this happens, now that might be kind of difficult to do. So the kind of poor man's way to do this is just use print statements. And this is what I mean, for a lot of my debugging, this is really what I do. You can really, it's a very kind of easy expedient way to try to figure out where in your code this is happening. But the most important part is to make sure you understand what your code is doing when that seg fault is triggered. So understand why it is the code led to that. Now in the toy compiler, I gave you the code so that if you copy the code properly, exactly byte for byte, the ASCII code, then you shouldn't have a seg fault. Yeah, so somebody points out that tracing through recursive functions is really hard. One really useful tool, well, debuggers are a really useful tool in general for doing debugging, but for recursive functions, it's really useful to have the stack trace. The stack trace shows you the nested set of function calls that were kind of pending when you hit that seg fault. And when we learn about functions and how recursion is actually implemented, we'll see why debuggers can easily tell you this stack trace, this trace of recursive function calls, because all these function state is stored on the stack. That's why it's called a stack trace. And we'll see that when we implement functions. But for tracing recursive functions, you can still do this in an expedient way with print statements. What you really want to know is the order of those recursive functions being called. So think about like a tree traversal. In a tree traversal, you're printing out each of the nodes when the nodes get traversed. And so if you know exactly when that recursive function is entered and exited, and you print that out, that's effectively a traversal of the tree. You're printing a tree traversal of the tree. So somebody asked, do you have to use the debugger to see that? And not necessarily. If you just have a print statement for each recursive function, that's a tree traversal, right? Remember what tree traversals were. Tree traversals were, I process the left and right child, and depending on whether it's pre-order, post-order, or in-order for binary trees, I print the current node, or I do my processing of that node. So if that processing is printing a tree traversal, then I just do a print statement inside of each of the recursive functions. And by doing that, you will see the order of functions that gets called. It can be kind of hard to see the nesting behavior. So you can add indenting, which you'll see for the AST printer that I'll give you next week. Or you can print when you enter and exit the node. And that will allow you to see the nesting relationship more easily. But for the toy compiler, that shouldn't be totally necessary. So let me see if there's some reasons why you might get a seg fault. So if the seg fault is happening, say, inside of gen code, that means something went wrong with the parser. If it's happening in one of your parser functions, like say it's happening in one of the in next token, then it's something wrong with your lexer. And now what's kind of very unsafe about C is that null is not only an error condition, but sometimes you intentionally have null to signal, say, the end of a data structure, which is the style I use here for these linked lists. And that's, that makes C particularly dangerous because it's hard to tell the difference between an intentional null and an unintentional one. And even when you have a null intentionally defining some invariant in your data structure, you have to remember to check that data, that condition, that there's a null, there's supposed to be a null at that point. And so it's very hard to tell the difference between, did I make a programmer error or did I just forget to check the conditions of my data structure? But for the toy compiler, the couple strategies you can use to kind of root out where that issue is you could do unit testing. So you could call next token and see and make sure that the lexer is actually doing what it's supposed to do, that it's producing something that is not null when you call next token. For the parser, you can make sure that all of these create functions the create functions are being implemented properly. So the create functions, these are setting up all the links between the AST nodes, just like in a linked list. So make sure that these links are all being made properly. That can cause a null pointer error. And for code generation, make sure that what's being passed in is not null already, although this is kind of checking for null. Make sure, yeah. So depending on where it happens, basically there's two main sets of data structures in this small compiler: the list of tokens, and each of those is a data structure where if you don't fill in the length, fill in the values of those structs, you could have a null pointer error. And the AST, which is a tree structure. And if you remember from CS1, you have to, just like a linked list, you have to set all those pointers to the next node or the child nodes. And in any of the places that use these data structures, you might get a seg fault, but the cause of that seg fault is the creation of the node, not the use of that node. Yeah, so somebody asked, create is basically like a constructor. Yeah, so it's C++. C++ is designed around making or automating the creation of data structures and the use of those data structures more safely. And so essentially, in C, we don't have classes and subclasses and constructors. So it doesn't mean you can't create objects. It just means that the language is not going to help you write those or enforce the correct usage of those. So for my C style compiler, I have these create nodes, which are basically, they're basically constructors. They're constructors for what you might think of it. They're basically objects. They're basically constructing objects. And in our case, the objects are defined using structs, and structs don't provide any help to construct them. In C, a C class is basically a struct. And in fact, the way they were originally implemented was compiling C++ to the C language. So the original C++ compilers were not generating machine code, they were generating C. And the way it worked was that a C++ object would be compiled into a struct that has functions associated with it through function pointers. And then the constructor is basically a convention that whenever you want to create one of these new structs, you have to have a construct function. Even if you've left it empty, the C++ compiler will automatically generate code that executes this construction function. Because we're using C, we have to do this manually. So all of these nice guarantees that C++ provides about the usage of these objects we just have to enforce those conventions manually. And so remember, all the way back in our first lecture, the whole goal of writing correct code is making the specification match the implementation. And in C, so much of that specification, we have to manually make that implementation match it. And so that's why you have to start very low level without any data structures and build those up yourself. Higher level languages like C++ provide automation in the language that provide not only automation for that implementation, but automatically checked specification. This is really what the type system can do for us. It can automatically check that our specification is met. So instead of, in this case, being vulnerable to forgetting to call a create function, the C++ definition of classes automates that specification. It says that anytime you have a class, there is always a constructor. And so there's no way to forget that. You still need to fill out that specification. You still need to define the constructor. But at least it provides you some automation for that specification. So someone asked, is it still common for C++ compilers to generate C? So no, that's not common at all. C++ compilers are now bona fide machine code generators. It's its own separate language, really. It's meant to be backwards compatible with C. That is, if you write a C program and compile it with a C compiler, it'll work. but it really is a different compiler and a different language. It just kind of subsumes C. And I think there may be even some very minor differences that I cannot think of now. But yeah, C++ is its own distinct language at this point. If you look at like an LLVM, the LLVM compiler toolkit or GCC, there are different front ends for C and C++ that generate the intermediate code. If you remember our architecture of a compiler, nowadays industrial compilers will generate intermediate code that is kind of in between the front end language and assembly. And yeah, C and C++ are very different at this point. So somebody asked, this might be a stupid question, so I don't think it's a stupid question. Don't be afraid to ask questions, even if you think they're stupid. I don't think there are stupid questions. And I won't say the glib quip to that, but I don't think there are stupid questions. Could C be updated to include objects? So this is actually kind of, I think this is actually a really good question. So C++ is C updated to include objects. That's what the point of C++ was in the first place. So objects are kind of popularly thought to be introduced in Smalltalk, which is a language where like everything is an object. I don't know too much about this language, but the idea is that it was a super simple language where you use this object paradigm to do everything in a language. All operations are object operators on objects. And Bjarne Stroustrup, I don't know how to pronounce his name, developed C++ as a way to have C all of the kind of efficiency and systems programming. And in his case, I think he was doing distributed networking and other kind of work in C. And he wanted a language that would use this notion of objects, but still have a C-like language, or at least have the benefits of C. There's a lot of criticism of C, but some of the benefits are that it is extremely good for doing systems code and low-level coding, which is one of the reasons why it still has not been unthroned as the kernel, the OS and systems programming language. There are good kind of attempts at safer languages for doing this, like Rust and Go and Swift, and they will, something like it will almost certainly take over from C. But C is kind of well entrenched in the systems and low-level coding world. I mean, even though the problems with it are well known, over the past decade or so, while it had seen a dip in popularity in C, being overtaken by JavaScript and Python and Java and other systems, other systems programming languages, it's seen a resurgence because of this whole Internet of Things world. And why is that? We have this kind of new set of devices that are extremely resource constrained. There are devices where you may not even have virtual memory. You may not even have an operating system. You just write one program that runs directly on the hardware. And so developers have just returned to the C language because all of the tooling is there. If you have to write a new Java virtual machine, it's probably not even going to fit into some tiny device. And so all of these developers for these IoT devices, well, we don't have an operating system. We don't have virtual memory. We can just write a one-off program in C. All the tooling is there. There's tooling to support, every processor out there and all sorts of platforms. All the ARM stuff is supported in C. And so C actually grew in popularity to be back into like the top 5 or top 3 languages. And you can actually look at this if you look at language popularity charts. It's grown in popularity because of this. So somebody says that there are tutorials for object-oriented coding in C. That's interesting. I didn't know about that. But it makes perfect sense. There are libraries that help you do this. So I think GNOME, which is a set of graphical tools for basically a windowing interface for GNU Linux operating systems. They have a whole object-based C library. It does seem counterintuitive, but I think this is why it's really important to understand how compilers work. Because in high-level languages, it's easy for us to believe the illusion of what these high-level languages are doing for us. It's easy to think that objects are something that the machine, something that computation how computation works. But really objects are a kind of human man-made conceit. I mean, it's all man-made, but it's a man-made conceit that doesn't actually run on the hardware. The machine does not use objects. You can't define an object at the machine code level and physically manifest that. It's physically manifested by the compiler or the interpreter, which creates data structures to represent those objects and then either interprets them with a virtual machine or compiles them to machine code, which doesn't have objects. And so in the same way that we wrote these data structures that contain information and behave just like objects, by having to write them by hand, we see behind the illusion, we see behind the magic trick, that how these compilers give us the ability to do objects. And so if you understand a little bit more behind the scenes, that can help make using objects more powerful. And so it won't seem as counterintuitive when you see if you look at these tutorials for how to do object-oriented coding in C, it'll seem less than counterintuitive when you realize that the compiler for C++ or Java is doing that for you automatically. So the compiler writers know how to do object orientation in C, and they're giving you an automated tool, a tool to automate that process for you. But just like any technical field, if you want to understand, say, how a car works, it's not enough to just look at the operational specification. Like if you understand how to drive a car, that doesn't tell you anything about how the car actually works, or tells you very little. And in the same way, if you really want to understand computing and programming, it's very valuable to understand, even if you can't implement it or understand the technical details, to at least understand conceptually how that language is designed and implemented. So Arduino, so somebody mentioned Arduino. I don't think, is Arduino, well, okay, so Arduino is a platform, a hardware platform. And I think the reason that someone says that they do it better than object orientation in C is that Arduino uses a Java-like language. And so Java provides a much easier usage of object orientation. Easier because you don't have to deal with pointers or references. That, I think, is probably one of the main keys to why Java is more intuitive. And if I'm not mistaken, Arduino is using a Java-like language. If anyone can correct me, maybe am I wrong about this? Oh no, it uses C++. Okay. So I'm not sure. So for that who pointed out or asked about saying C, object-oriented C is counterintuitive when Arduino does it better, can you give a little more detail? So by Arduino, do you mean the programming language? So it uses C++. I think there's also this thing called processing, which uses Java, which that's where I may be confused. That was unrelated. Okay. Okay. And so there are other attempts to add object orientation to C. So there's Objective-C, which was, I guess, made very popular by iOS, the Apple operating system, which I guess due to its, next step was using Objective-C. But that was another attempt to design a extension to C that allowed for object-oriented programming. Okay, so that was a nice little tangent. So somebody mentions that structs are basically objects. So yeah, structs are objects are structs with function pointers or with functions associated with them, and some protocol for constructing them in C++, for instance. Okay, so that was an interesting tangent. Let's get back to the main part of the course. So other questions on the compiler, on the toy compiler? All right, so let's get into this mind-warping notion of compilers. So we just spent, just last week, we looked in detail about what compilers do. They're already confusing enough because a compiler itself is taking, a compiler itself is taking source code and producing object code or target code. it's generating code. So you have these three languages to try to think about at the same time. The language that the compiler is processing, is inputting, the language that it's generating, and also the language that the compiler is written in itself. So and the compiler itself has to be compiled. So it's very confusing to kind of think about all these different languages at the same time and how they work together. And to throw just another level of complexity here, going back to our diagram, just to throw another piece of complexity in here, here's these C files here are our compiler source code that gets compiled into a compiler. That compiler that we compiled takes source code and generates target code. And it turns out that writing a compiler, as you've seen with just this toy compiler, can be tedious and difficult. So parts of these compilers can actually be generated. And so with compilers, we specify the phase of the compiler that we want to write. And this compiler will automatically generate the C code for us for that part of the compiler. And there's been, as I was kind of going back and researching for these lectures, I was kind of interested to see how far this compiler work went. And there's actually been some pretty interesting work decades ago, like in the 70s, where they try to generate the entire compiler. For this class, we're going to look at the sort of common tools, the prevalent tools that can generate the lexer and parser, and we're going to handwrite the rest of it. So somebody asked, is CodeGen all we need to write? Well, that's all we need to write in C. So CodeGen's all we need to write in C, but for the compilers, just like a regular compiler, the compiler is not going to know what it is we want to generate. We still need to specify what it is that we want to generate. And so and part of the idea of having high-level languages, including compilers, or just regular compilers, is you can think of C as almost a way to specify the computation that we want to do, and the compiler is generating machine code to actually do that computation. And so from the compiler point of view, we want to sort of move closer towards writing just specification and not having to write code. Because remember, the whole goal of writing correct code is making the implementation match the specification. If we can just write the specification itself and have the implementation automatically generated, then that's great for making the implementation match the specification. Because then we just have to worry about how do we specify the problem, and then the actual implementation is done for us. And there's a lot of interesting research along these lines. So the chair of our department, actually, Gary Levins, has done a lot of foundational work on doing formal specification of software. And his work has shown that some of the most famous stuff is in Java, where you can define a mathematical specification of what the code should do, and then you can automatically check to make sure that the specification matches the implementation. There's also more modern work on not only using specification to match the implementation, to check the implementation, but to actually write a math proof of the thing you're trying to do, whether it's a sorting algorithm or a search algorithm. Write a proof that it's correct, and then use that proof to automatically generate code. So this is taking the notion of specification to like an extreme, where you just write specification and the implementation is automatically generated. So, okay, so another little tangent on compilers. Would that be an example of a type of evolutionary algorithm, somebody asked? Not really. Evolutionary algorithm is a strategy for writing algorithms. You may use an evolutionary algorithm to find an implementation. And there are actually cases of using these kind of iterative algorithms for finding the right implementation. So there's some famous work from about a decade ago on program synthesis, or is this program? Well, is this called program? I can't remember there's all these like new names for these fields, but there was a famous work where, it was automatic patching. So program synthesis is also related. There was a famous work from 10 or 12 years ago where the idea was we want to automatically patch and do automatic bug fixing, automated I can't remember the term. I guess it's program synthesis is the term if you want to look this up, where they would take a bug, you know that there's a bug, and then you basically just automatically generate random fixes to that code and then rerun the test. And if the test was successful, well, voila, you've automatically fixed your code. And they would use, and the early work of this would use evolutionary algorithms, where they just generate a bunch of patches and cull the ones that were not fixing tests in the test suite, keep the ones that were fixing them, and then start generating code based on those previous fixes. So certainly evolutionary algorithms are just a technique for basically having basically dealing with using randomly generated stuff to solve your problem. But it's not, yeah, it's putting the monkey on a typewriter through. Exactly, yeah. So this is really how a lot of these algorithms work. In fact, any statistical algorithms, including like machine learning, are also kind of using a similar approach, where you're just training through lots and lots of data to make a statistical model. And evolutionary algorithms are, they're kind of related to the same, using randomization to fill out a statistical model. But no, evolutionary algorithms are a technique for writing algorithms. This is separate from the idea of taking a specification, the notion of taking a specification and automatically generating an implementation from it. There are many ways to do this. You don't necessarily have to use statistical approaches to do this, although this is one popular way to do this. There are ways to do this instead of using a test to see whether you've gotten the right code, you could use a proof to guarantee that you've gotten the right code. Kind of in this, what I was talking about with Dr. Levin's specification, Java specification. If you have that specification ahead of time, but not the code, there are techniques for generating code from the specification that don't necessarily rely on randomization. Even if you have randomization, you can at least check using a proof whether that specification implementation matched the specification. Okay, so so we have a couple minutes before we should take a break. So let me just go through a little introduction to what these compilers are going to do for us. Yeah, this is great. So I'm giving you kind of keywords here. If you're interested in this, just Google it. There's some good resources on program synthesis and specification versus implementation, automated theorem proving. These are the kind of keywords you want to look up. And all this is very much in the research realm right now. I don't know a lot of industrial stuff that is doing this yet, but we'll definitely see it over the next 10 years, 10, 20 years. Okay, so remember, our lecture was pretty tedious. We had to worry about all of the, so that picture is ugly. Let's look at the actual code. So if you remember what the lecture did, it was pretty tedious. We had to worry about file IO. We had to loop over each character one at a time. We had to check each individual character. And as we'll see, when we have languages where a token may be more than one character, like an identifier, we'll actually have to match a pattern that defines what an identifier is. So how do we tell the difference between an identifier and a keyword or an arbitrarily long number? Well, we have to have some pattern recognition that can check, well, okay, an identifier always starts with a letter. So it's an identifier followed by any number of letters and numbers, but as long as there's no spaces in it, because if there's a space, then in C, that means that that means a new identifier or a new number. And defining all that in code and trying to do that in code is extremely tedious. So that's why this semester I'm not having you actually write that. Instead, we can define these patterns of these tokens. We can define these patterns of tokens using regular expressions. So who's heard of regular expressions before? So this is something that is pretty common. Yeah, so I think a lot of people will have heard of these. And so this is something from the kind of theoretical and meta mathematics world that has made its way into the standard toolkit for programmers. Yeah, so the language you use it in is sort of irrelevant. The concept of regular expressions is a kind of computational theory concept that can be used in any language. So in any language, as long as you have a library for taking regular expressions and generating pattern matches. The main thing I want to get across in this class is the kind of theory behind regular expressions, why they work, and how they can be automatically generated. Okay. Let me just, before we take a break, let me just show a little bit of what these lecture specifications look like. So on the left-hand side here is a pattern we want to match, and it's a pattern written in regular expressions. If you haven't heard about regular expressions yet, don't worry, we're going to go into it. But just realize that each line of this specification is saying, here is the pattern we want to match. And this pattern defines all possible tokens for that, all possible patterns, or all possible series of characters that match that token in our language. So this is SimpleC. So I changed this a little bit, but I'm not used to showing the toy compiler. I'm showing SimpleC, so it's a little bit of a preview. But this pattern here, for reasons we'll get into, is saying an identifier. So here on the right-hand side, this is what we want to do when we match the pattern of an identifier. It's saying this is an identifier token. The pattern is saying, well, anything that starts with a letter and then has any number of letters and digits following it, that is, in our language, an identifier. Here, this is saying any sequence of one or more digits, well, that's an integer constant in our language. And so in the same way in our toy compiler that we would read in one character at a time and loop over each character, checking what kind of character it was, and using that to create tokens in our compiler, we can kind of automate that process by just specifying a pattern that matches a token. And as long as we see that pattern, we create our token whenever we see that pattern. Okay, so that's a little preview of what we're going to see in the next hour or so of our lecture. So let's take a break and let's come back at 11:30. I'll try to make these, actually an hour and 15 minutes. But there's a lot of tangents we go off to. So hopefully you enjoy those tangents enough to restrict our break by a couple minutes. So let's come back at 11:30, and whoever has questions, I'll stay here for the next 5 or 10 minutes. So if you have questions, feel free to ask them now, and then I'll take a little break, and let's reconvene at 11:30. Oh, somebody asked, is SimpleC basically C without all the libraries? Not quite. So the libraries are not part of the, well, so in some sense they're part of the language definition, but they're not part of the language that the compiler processes. And so we'll see this when we get to machine code generation, when we actually start seeing how in the Unix programming environment, how libraries work. But in the definition of the C language, at least from the syntactic and semantic point of view, the libraries are not part of that. So the libraries, yeah, exactly. So the libraries are, so once you have the C compiler, you have something that will take C syntax and generate machine code. The libraries are just a bunch of function definitions that you write in the C language. And the reason that there are standard libraries is just by convention, any system that has a C compiler should also have implementations of these libraries. And so in that sense, they're part of the C standard, but they're not part of the C language per se. So the C language itself can be thought of as the specification of the language constructs and their semantics, that is how they should be translated into machine code, or how they evaluate, how they evaluate values, what happens when you run them. But the C standard libraries are, in some sense, part of the language because they add new words to the language that you can't use anymore. So in that sense, they're part of the language. There's a really excellent talk by this famous computer scientist who worked on the Scheme language and the Java language. And why can I not remember his name right now? So he had a really nice talk called Growing a Language by Guy Steele. That's his name. Where he talks about this notion where you have the core language, the set of constructs, and then what a programmer does is they actually add new words to that. Like the language provides mechanisms for extending the language. And so you can think of a function definition as a way to extend the language. And so while the compiler does not provides you a set of the sort of language per se, the actual constructs that it translates, the language designer provides you mechanisms for extending the language, that is, adding new words to the language or adding new types to the language. And so this is a really nice, I think, a really nice view of language design. And I should probably post this. Maybe I can put this in I should put this somewhere. So for those who are interested, can look at this. And he does a very cute thing in the talk where you'll see it. It's a little surprise where, the way he talks in the beginning sounds very stilted, and there's a very interesting reason for that. He's making a kind of point about large languages versus small languages. And I'll let you watch this and see his point. List of tools with tools I'd recommend. Oh, that's a good question. I don't. I could make like a blog post or something on the tooling I use. Let's see. Okay, let me make a. I do have kind of a blog that I rarely use or update. So Emacs is my main program editor. Biovu is what I use to have multiple like windows and the command line. So I can this is really particularly useful for when you're using a remote system. If you go on Eustace or something and you exit, all of your processes are going to get halted. If you want to leave something running and you don't want to like lose your bash history, you can use Biovu or Screen or Tmux. These are tools that are like bash session managers. And so so you see at the bottom here, I have many these numbered bash windows here. I can switch these all on the keyboard. This is one program running that allows me to switch between multiple command line prompts instances of bash. What else do I use? I mean, there's all the tooling from last time, Make and GCC, but those are kind of like the standard Unix tools. I mean, grep, yeah, just all the kind of tools that I talked about in the second week, the command line tooling. That's really a lot of what I use. Because I want to be able to work on servers, I kind of tried to have everything done from the command line. And so a lot of my tooling, I just use the command line tools, the Unix tools. But yeah, I can try to fill this out and make a post eventually. It might take me a little while though. All right, I'm going to take a break myself. I'll be back in 3 minutes. Sorry, I was muted. Sorry about that. I've just been talking to myself for the last couple minutes. So welcome back to System Software. Let's continue on talking about compilers. Welcome back, everybody. Okay, and so we left off before the break. We were talking about how we can automate the generation of a lexer. For the toy compiler, we had to do the tedious job of doing file I/O, looping through each character at a time, checking what kind of character it was. And I designed the toy language to only have single-digit tokens. But if we have tokens that have multiple characters in them, like identifiers and hexadecimal constants, integer constants, keywords, then we have to check each of those characters one at a time to see which token we should generate. A lexer generator turns this into a problem of specification, or at least something closer to a specification. Instead, on the left-hand side, we say, here is the pattern we want to match. And on the right side, in these curly braces, we write some C code to say what we want to do when we see that pattern. So in this case, I'm matching a pattern that says, if I see any ASCII character that is the digits 0 through 9, then call A to I to convert it to an integer, and then just return an indication that this was a number token. Similarly, for semicolon, I can say if I match a string that just has a semicolon in it, then return the semicolon token. In this case, I just use the ASCII code to refer to the semicolon token. And here, this one is a little bit more interesting. This is saying if I match either a plus symbol in ASCII, a minus symbol in ASCII, a star, or a / in ASCII, then for all of these, produce an operator token, indicate that it's an operator token. And this code here is just saying, well, save the text of that, because if you remember, in our program, we had to call, we had to write code that would not only do this matching, but would create a data structure that held on to the original operator. So we not only had to match the input to make sure it was an operator token, but we had to create the data structure. All of this can be largely automated by just specifying the patterns of the tokens and then putting a little snippet of code to say, what action do we want to take when we see that pattern? Is this making sense? Does this make sense? Any questions kind of in general about the idea of doing this? The main idea is we can replace the tedium of writing code that does file I/O, loops over each character, has to try to match what the characters are, or which tokens these characters are part of, generate a data structure that holds on to these tokens. Instead, we write a specification file that on the left-hand side defines the pattern that the tokens, a pattern to match those tokens. And on the right-hand side, we write a little snippet of code of what action we want to do when we match that token. So this, so this file on the left here, this is a flex file. This is the flex tool. So Bison and flex are two different things. Yeah, exactly. So this file here on the left, this will do basically the exact same thing that we did on the right code. So somebody asks, I don't understand the question, would we have to read code from a file and temporarily add it to our code? So the way this will work is if we look at our diagram here, the way this works is now, instead of writing this, my iPad is frozen, but instead of writing this lexer.c by hand, we write this lexer.l file, this flex specification, which I was showing you. We generate this C code. It'll generate the C code automatically for us. So this code on the left here, these 3 lines are basically doing the same thing as these many lines, these 50 or 60 or so lines, more or less. And the reason this works is because this job of Lex, of looping through each individual character and trying to group these characters together and match the patterns of the tokens of our language, we can specify this pattern matching as a single regular expression. And a regular expression is a way of defining patterns of sequences of strings. And so one example of this is just saying, well, if it's one of these 4 things, which, remember last time we were like, should this be if statements? Should this be a switch statement? Should this be a table lookup? This process of doing this pattern matching can be automated. And we can instead, just like we'd have a compiler which takes C and generates machine code, we can use the regular expression language to define these patterns and automatically generate C code which matches that pattern. Yeah, so somebody asked, so this is a nice segue to the next part, the next thing that we generate. Where do the values go when we generate this? So just like our toy compiler, remember the parser called the lexer. The parser needs to know the sequence of tokens in the input file and then create a syntax tree out of that sequence of tokens according to the grammar of our language. And so when we look at Bison, the parser generator, the Bison and Flex tools interoperate. So there's a bunch of conventions for operating together. And this snippet of code, when it says return, it's actually passing this information to the parser. And somebody asked about this YYLVAL thing. So this is also part of the interface to Bison. As we'll see in Bison, every token and every grammar construct has a value associated with it. This L value is where we store that value. So let's look at Bison and to see how this actually works. But basically the code on the right here, so this echo is just a built-in thing that will print out. This is just for printing out what we read in. This is also something built into Flex. But the relevant part on the left here is that we tell whoever calls the lexer what token we saw. And if we so choose, we can save the value of what we saw, either in this case as an individual token. So YY text is the lexeme or the series of characters that were matched by the regular expression. And YYL value is the value that we define. So we're saying that if we see one of these 4 strings in the input, then we want to tell the parser that the value of this string is just the first character. This is a kind of little hack because I know that each one of these strings has a single character in it. So don't worry too much. This is a little bit of a sort of a hacky detail. But as somebody just pointed out, if we match one digit between 0, that's one of the ASCII codes 0 through 9, then the value is exactly right, exactly as your fellow student said. We want to set the value of that to be the integer representation of that ASCII code, and A to I is how we do it. So this is starting to get into the kind of semantic definition of our language. And this is where so this is not something that's built into our specification. This is something that we write as the language designer. This is something that we write as the specification. This Flex is just a tool to help us turn some of the tedious tasks of lexing and parsing into a specification task that can be automatically generated. And so even though, so this is kind of the cool philosophical part of compilers and languages in general, is that even if we can automate the process of generating implementation, we still need the specification itself still needs a representation. So even if we can just use formal math and have a rigorous proof for defining the specification of our language, that specification itself is still in some representation. It's you know, even if you subscribe to the kind of Platonic philosophy of these forms, you know, being these abstract ideas, if we want to manifest them in the real world, they still need a physical representation. And so these specifications themselves in the computing world still have a language for defining them. Even if your specification is just an ASCII text file where you write human language saying, well, this is what I want the program to do, it still has some physical representation. If we want to systematize the specification so we can automatically generate implementation, then we need some well-defined language for doing that. Regular languages are how we specify patterns of strings, patterns of tokens. And I'll give you readings in the Dragon book. We're not going to go into too much detail about the language part of it. But if you look at the readings I give you in the Dragon book, regular languages themselves have a grammar and have a semantics. But for us, from our point of view, we're going to kind of stop at the language implementation point and just assume that we are given the Flex tool, which and just learn a little bit about the regular language and how they work. And you're not going to have to write this. I'm going to give you the Flex specification for SimpleC. But I think it's just interesting to understand how you can define a new specification language that can be used to generate code, and then that code can be part of our compiler. So somebody asked what YYWrap is. So this is kind of details of the Flex tool. This is what happens when you finish reading a file. YYWrap will be called. It basically allows the Lexer to read in multiple files instead of one file at a time. This is all kind of the systems part of how Flex works. So okay, so that's the basics of what Flex does. All right, so there's already kind of a comment here that tells you what this does. So I mean, does anyone want to kind of comment on what they think this specification does? So remember, the left-hand side matches a pattern. The right-hand side is some code that defines what we do with that pattern once we wrap it. Yeah, so it's exactly. So it's matching white space. So somebody said tabs, new lines, don't even bother with white space. So in the same way that we match tokens in our language, we can match the stuff that we don't want to be part of our language, like comments and white space. And so for Toy compiler, all we're doing is saying if we match any of these non-printable characters, spaces, tabs, I don't even know what /v is, new lines and page form feeds, then we just want to do nothing. We want to, well, echo prints it out, and then we don't want to return anything. And so what will happen is the parser by convention will just, you know, there won't be a return value yet. So the Lexer will just continue lexing. This is kind of our trick. Basically the same trick that we did here, where if we saw white space, we just called lex again. This is on the left-hand side, this is in effect doing the same thing. And we're also just going to ignore characters that aren't even part of our language. So if we accidentally put, you know, a money sign, this will just get skipped over, basically. Okay, so that's Flex. And if you want to learn more about this, there's this nice website called Compiler Tools. Why won't it go there? Okay. That has a ton of resources on compilers. And I won't go into too much detail about like the input and the format. We'll talk about regular expressions in a couple of weeks when we talk about the formal theory behind them. But yeah, basically this is the layout of the file. So no, you're not going to have to learn. I'm going to give you all the Flex files you need. You're not going to have to learn the details of its system implementation, of its like interfaces. I'm going to give you all that. I just want to kind of show you this so you can see the equivalence between the code we wrote and the Flex tool. Okay, so if you're interested, take a look at that. I've put links in the lecture notes for doing that. You don't have to learn the details of how this works, but if you're interested, you're curious, by all means, take a look at this. It'll show you how all the formatting works, all the interfaces. But I really want to get on to the Parser Generator. I think the Parser Generator is a little bit more interesting. You're going to have to work with this specification a little bit more. Okay, So in our toy compiler, we wrote this parser.c. We had to, basically define the grammar as a series of recursive functions, and also define a bunch of AST creation nodes. And so we can also, in the same way that with flex, that we can define a regular expression and then take some action in C whenever we match that pattern, we can do the same thing with C code, with grammars. So Bison has the same kind of idea, where on the left-hand side, we define some grammar construct, and on the right side, we define some action that we want to take, some C code that we want to run whenever we match that. Now, this is a little bit more complicated than the lexer. So the lexer is just matching sequences of characters. With the grammar, we're trying to match the hierarchical syntax of the language. So to put the parallel here, let's take a look at our parser from last time. So the key elements, the key ways that this recursive set of parsing functions defined the grammar was to define a function for each construct in the language, and this corresponded to one node in our syntax tree, and then recursively call each child node or each element of that grammar construct. So if a statement list is composed of a statement followed by another statement list, then we defined a function called statement list, and inside of that function recursively called the statement function and the statement list function. And for the statement grammar construct, we define a function called parseStatement, and inside of it, it contains just a single expression construct. And so we recursively call the expression construct. And for the expression construct, we have a function defining the grammar of that expression construct. And then inside, we call the three symbols that define an expression construct. You guys with me so far on that? So you can see there's this kind of pattern to defining grammar constructs, and that's, we have the name of the grammar construct itself, and then all of the constituent parts that make up that grammar construct. In the same way that a sentence is made up of subject, verb, object, and a subject is made up recursively of, maybe noun, phrase, article, adjective, noun. A verb might be made up of either a verb alone or a verb plus an adverb. And so all of these different syntactically legal programs can be defined as a grammar. And the way we define a grammar in Bison is on the left-hand side, we have a production. A production is composed of the symbol name, like here. Well, let me look at statement list since that's what we have. Actually, let me look at expression. So here we have, on the left side, we have the statement, and separated by a colon is the constituent parts of that construct. So a statement is comprised of a single expression symbol. An expression symbol is comprised of three other symbols. In this case, three tokens: number, operator, number. And so this whole specification here is called a production. A production maps some syntactic unit in the language, some construct, to other symbols in the language, to the parts that make up that construct. So is everybody kind of with me so far on this? In the same way the lexer is specifying a pattern, this is a kind of pattern definition for hierarchical syntax. I'm getting silence from the chat, which could be either a very good sign or a very bad sign. So questions on this so far? This is dense. Yeah, okay. So this is, we'll see this in a couple weeks when we actually get into how this works, and when we get into grammars. So this is, we can define the syntax of a construct in our language using a production. And a production maps the name of the construct to a sequence of symbols. Those symbols define the components of that construct. So an expression, so in natural language, an expression is a binary arithmetic operation. And well, so what is a binary arithmetic operation? Well, a binary arithmetic operation is some number followed by some operator followed by another number. And so we define the pattern of that expression construct as the expression keyword followed by a colon. And the colon says, here is going to be what comprises that construct. So the expression is comprised of number, operator, number. And in the same way, a statement is just comprised of an expression followed by a semicolon. And a statement list is comprised of either an empty, either nothing, empty, and this is going to be a confusing thing we're going to have to go into a little bit more theoretical detail in a couple weeks. But a statement list, just like a linked list, ends with a null. A statement list either has something empty or it's a statement followed by a statement list. And so this is basically like recursing over a linked list, where a linked list ends whenever you see an empty node in that list. This will become a little clearer when we look at grammars more theoretically. But I just want to kind of draw a parallel here between each of these productions corresponds to one function in our parser. And so this is kind of tricky to wrap our heads around, because in order to kind of understand why these set of recursive functions work, it's important to understand how grammar works and how hierarchical syntax works. And so since I'm kind of delaying the theoretical presentation of that, we'll kind of just have to kind of do this intuitively. So if you understand the toy compiler, sort of mechanically how it works, we can automate the specification of that. Yeah, I have sample inputs. I'll show that. Well, you have a sample input from the toy compiler. It's the same. But just in the same way that we drew a parallel between the Lexer implementation and the Lexer specification in Flex, there's a parallel here between our toy compiler implementation, where we wrote this series of recursive functions that outlined the syntax tree. We can specify that in a grammar in our Bison specification. So here we have 3 grammar productions in our Bison specification. One for statement list, one for statement, one for expression. This corresponds to our 3 recursive parsing functions in our toy compiler. The statement list, our statement, and our expression. And there are 1 for each of these. Okay, so getting some questions about some of the details here. So somebody asked, can we automate both our Lexer and Parser with Bison? So we automate both of these. We automate the generation of both of these phases of the compiler. The Lexer is automated with the Flex tool, and the Parser is automated with the Bison tool. So there are 2 separate tools. They interoperate to give you both the Lexer and Parser, just with one function call, basically. And as somebody asked, this parser.y file on the left, this is a YAC file. So YAC was the earlier tool. YAC stands for yet another compiler. YAC is the Parser Generator. Bison is the GNU system implementation of the YAC. YAC was a Unix tool from the AT&T world. And Bison was a re-implementation of this. And so it's, it's a very punny joke, because a YAC is a type of ruminant, I guess, and a bison is another type of it. And of course, a GNU is yet another type in that same family of animals. And so, yeah, the GNU people had a great time with all their puns on this. But the main thing I want to get across is that without going into too much detail about grammars, just think of grammars as a recursive tree walking algorithm. And we can specify the pattern of the constructs that we walk, the tree that we walk, using these 3 grammar productions. And so with that, yeah, I think Josh went into a little bit. So it's good to go to labs because Josh covered in more detail grammars last week. And so if you attended the lab or watched the talk on that, he went over grammars a little bit more detail. And so as somebody asked, will this generate many more lines of C code? Yes, this will generate a ton of C code because of the computational formalism that's used to generate this parser is actually not, for Bison, it's actually not generating recursive function calls, it's generating a pushdown automaton. And we'll talk about it in a couple of weeks, but it's another, yeah, we'll get to the theoretical stuff about what it generates. But from your point of view, from the user point of view, think of this as, well, here is the same thing as a recursive function call that's saying, I'm defining the statement list function, and it's recursively calling statement and statement list, or it's recursively calling nothing. And this is the same thing as what we wrote by hand in our toy compiler. And remember, the thing that we returned, when we did this recursive tree walking, each one of these parsing functions created a new AST node. And this little curly braces, in the same way Flex was specifying an action to take once matching the tokens, the Bison file is allowing you to match this grammar construct. And whenever we recursively parse this grammar construct in our input file, this is the action we're going to take in C when we do that. So let me get to questions in a second. Okay, so let me go through the kind of syntactic details of what this little snippet of C code looks like, because it probably just looks like gobbledygook right now. Okay, so on the right-hand side, what did we do? We created a statement list and we returned it. We returned the statement list, we returned whatever was created by the statement list, and we passed in the results of recursively calling the children, recursively traversing the children of a statement list. The two children was a new statement and a new statement list. And we create the statement list that we're parsing in this function by making an AST node that has both the statement and the statement list that we recursively parsed. So let me say that again for the statement, so it makes it a little less confusing. The list thing, this recursive list makes it confusing. But basically, the statement function recursively calls expression to parse the expression. That returns an AST node. So we don't care how, don't worry about how that's implemented or how that works. Just by the specification of how parse expression works, it returns us a new AST node. And when we're done with this statement function, we create a new statement node. And that statement node has as a child the expression node we created when we recursively called parse expression. Any questions on how the statement parsing function works, what it does locally from its own, assuming that parse expression works already, assuming that create statement creates an expression node with an expression, creates a statement node with an expression as a child. Is everyone on the same page about how the parse statement node works? Or at least what it does, assuming that parse expression and create statement are already implemented. Questions on that? Okay, at least one person is good on that. So let's look at the parallel in our Bison specification. Putting statement here on the left of the colon is like defining a new recursive function. On the right side of the colon is like doing the recursive calls to other parsing functions. So this is saying recursively call the expression parser and return whatever its node is. And if we see a token, just do what we did here and match to make sure that that is the next token in the input. Same code that we wrote here on the right-hand side. Then when you're done doing those recursive calls and matching any tokens in the input, then run some code. And the code that we run here is this double money sign here is basically saying, return this value. This is the return value. And here's the value that we want to return. We want to create a statement just like we did on the right-hand side. And here is the trick. This money sign 1 is saying, go to the first symbol, which is expression, and use its return value. So in the same way that on the right-hand side, we recursively called the expression parser and saved its node, in Bison, you do that by referring to this money sign 1 variable. So this money sign 1 variable is the return value of recursively calling the symbol on the right-hand side of the colon, recursively calling the expression. Does anyone have questions about this parallel? Do you guys see this parallel between the two? Okay, at least one person does. That's good. So if we want to say, so somebody asked, yeah, it's a lot to take in. So I think when you write the toy compiler and when you look at the Flex and Bison specification of it, hopefully, I think that will help. And then next week, when we actually start on the SimpleC project, I'll walk through implementing a couple of grammar constructs for SimpleC, because the SimpleC specification is much larger. So I really want you to understand why this works for the toy compiler before you start getting into the SimpleC, because it's much larger. Yeah, just rewatch it. And I really recommend for those who are sort of hands-on learners like I am, write the code. I'm going to give you the code for the toy compiler, the compiler version of the toy compiler. I'm saying compiler a lot. Okay, so why don't you need money sign 2 for the semicolon? So by the same notion, on the right-hand side, we don't care about the semicolon anymore. The semicolon helps us ensure the syntax, but when it comes to the abstract syntax tree, looking at the semantic, that's going to help us process the semantics of it. We don't actually care about the semicolon. Another way to look at it is the semicolon has no analog in assembly. There's no interpretation of the semicolon that is required in order to produce an assembly code equivalent of the program. So the semicolon is just a kind of syntactic artifact that allows us to match the syntax of the input. And we can see that in the parallel on the right-hand side. Yes, exactly. So once we realize that there's an expression, we can just create an abstract syntax tree. So instead of the concrete syntax, which has all of the tokens, we can abstract away some of the details of the syntax into just what we need in order to create assembly code. And we see that reflected on the right-hand side here. When we created this statement node, all we needed was the expression to create that abstract syntax tree. So by the same notion, on the right-hand side of the production, we only use money sign 1 for the expression to get the value, the AST value of the expression. And this double money sign is essentially the return value. So yeah, rewatch this, handwrite this stuff, look at the code, play with it, compile it, run it, to kind of wrap your head around this. But in the same way that Flex is doing pattern matching and allowing you, the language writer, to specify what code gets run when you match that pattern, we're doing the same thing, but for a grammar. And that makes it confusing because grammars have this hierarchical syntax. So we need a way to specify the recursive nature of these patterns in the input. In the same way that we have these series of recursive functions, we have these productions that specify the recursive behavior of the program. So yeah, rewatch this, pause it to kind of digest this. Now, somebody asked about money sign 2, and that's a really good extrapolation that you did. So this money sign 1 actually refers to each symbol in the production. So money sign 1 refers to the return value of recursively calling statement in this production, and money sign 2 refers to recursively calling the statement list production. So forgetting about the recursive, forgetting about the fact that this is self-referential, in the same way that we created a new statement under the statement production, here we're creating a new statement list under the statement list production. And we're doing it in the exact same way that we did it in our handwritten parser. This double money sign is saying, here's the return value for statement list. Here is how we create the value, we call the create statement list. And here is what we pass to create statement list. So create statement list creates a new AST node with 2 children. And we get the values of those 2 children from the recursive calls to statement and statement list. In the same way on the right-hand side, we recursively called statement and statement list, saved those AST nodes, and then called create statement list to create a new node. Let me actually draw a snippet of this. Whoa, this is not at all robust here. Let me actually draw a little snippet of this process. Yes, so somebody's asking, we always create the children before the parent. That's absolutely right. So this is called bottom up. We're creating the leaves of the tree, and then it's kind of like a post-order traversal. We process the leaves first, and then we bubble up the recursion to the parent. But unlike a traversal where we already have the tree, the parser is actually creating the tree as it goes along. So just let me show you the statement list recursion here. So when we call statement, we get some node. So this is in the middle of parsing. So when we're in the statement list, the Bison will match that we'll do pattern matching to say we've seen a statement here, and the result of that is creating this AST node. I'm sorry, when we see a statement. And the next thing we'll do, it will match the statement list, and that will create a statement list node. So forget about now what the children of that are. And that's what's happening. That's what's happening here in our toy compiler. And similarly, that's what Bison is automatically doing for us when we specify that a statement list is comprised of a statement and a statement list. AST stands for abstract syntax tree. Syntax tree is what we saw with is here. This is a syntax tree, or a concrete syntax tree. And an abstract syntax tree is a syntax tree with information removed that we don't need for actually generating assembly code. Okay, so we've created these recursively created these 2 AST nodes. And that's what Bison is automatically doing for you. It's managing this process of creating them. And the last thing we do when we finish parsing a statement list is to create a new statement node. That's what the create statement function does. And we pass in the 2 child nodes, statement and statement list. And so what's happening in the data structure is it's creating these links, and it's creating this tree structure here. So this reference here, a reference to this statement node. Oh, you can't see the pointer. That's weird. A reference to that statement node is what gets returned by the statement list function. And the way we specify that return value in Bison is to use this double money sign. So the syntax is very old school. This is like decades old syntax for Bison. But that's essentially what it's doing. It's just saying, this is the return value I want whenever you match a statement list in the input. Now, I think if you can wrap your head around syntax trees and parsing of syntax trees and walking of syntax trees, then this, I think, may help a little bit understand recursion. So rather than having to think of just any recursive function, think of recursion as just outlining a tree. Parsing is a little tricky because parsing is actually creating the tree as you go along. But effectively, a parser is just outlining the grammar, is just walking. The grammar is like a schema for defining a bunch of different trees. And the parser is outlining one instance of that grammar, one tree. But if we look at these semantic actions, I'm sorry, if we look at, I'm using terminology I haven't introduced yet, but if we look at these little snippets of C code, or we look at the recursive implementation of this, it's really just traversing a syntax tree and creating AST nodes. And what makes recursion truly hard to reason about is that there's self-reference in recursion. So here, the parse statement list is recursively referencing a statement list. That's, I think, what makes recursion really hard to think about. Because if there was no self-reference, then recursion would not be recursion. It would just be function calls. And if you understand function calls, you pass in parameters and you get return values. If you understand that, then without recursion, this parser is much simpler to understand. It's the self-referential part of recursion that I think is the hardest part to understand. And the way to make this a little simpler is that don't think of it as self-recursion. Think of it as a way to, think of it as a different AST node that happens to have the same name. So when we are creating this statement node, it's taking some, oh man. Technical difficulties. If we look at a single run of the statement list function, parse statement list function, it's creating a new statement list. And it's creating a new statement list that has two children, statement and some other statement list. So let's call this statement list 1 and statement list 2. And if we happen to parse yet another statement list, then we get a completely new AST node. Even though it has the same name in our code, it's really a completely different data structure. It's statement list 3. It has a new reference. It's not the same data structure. The code uses self-reference in order to define this kind of iterative structure, but the data structure itself is a different node. And so if this parser is looking at multiple statement lists, even though the parsing function is all called parsing statement list, it's really outlining a unique node in that tree. Does this kind of make sense? Is this at all helpful in understanding recursion? Okay, okay, I'm glad that's, okay, good. Okay, so this is clicking. Okay, that's really good. And so when we look at how recursive functions are implemented, because they're a conceit of the input language, the machine does not know about recursion. The machine does not run recursive stuff. We have to actually emulate recursion in our implementation of the language. We'll see that even if you look at something like a factorial function, we can actually conceive of any recursive function as a kind of iteration over a tree data structure, tree or a graph. And it's for me, it makes it a lot easier to understand recursion. Okay, so that's the idea here. So when we have this grammar definition, if you can wrap your head around this kind of iterative grammar definition, then Bison, even with its kind of esoteric syntax, is much easier to write than writing a parser. We don't have to worry about reading tokens. We don't have to worry about advancing the look ahead. We don't have to worry about matching tokens. We don't have to worry about the recursive calls. All we have to do is say, if we see this particular grammar construct, we just want to create a new node for that grammar construct. And in this class, we're not even going to worry about implementing the language using the parser. We're just going to create AST nodes. So all we have to do is fill out these little snippets of code to create the new AST, to create the right AST node for that grammar construct. That's the whole, we turn this whole problem of parsing that we had in the toy compiler into one of, well, let me define what the grammar constructs are using productions. And then to create the AST, we just define a little snippet of code that calls the AST creation function and just pass the resulting AST node from the right-hand side of the production, the constituent parts, from statement to statement list, and set that to be the resulting value from this grammar production. Yeah, so I got a couple of questions here. So somebody's asking, will our main C file still use the AST to write our target code? Yes. So main will, yeah, we still need to write the code generation part, which traverses this tree. But the whole job of lexing and parsing will be taken over by Bison and Flex. We're still gonna write these little, so these are called semantic actions. We're gonna write these little semantic actions, these little snippets of code in curly braces that are the behavior that we want the parser to take when we match something from the input. We're gonna write that to just create an AST, and then we're gonna use that for code generation. And somebody asked, but in our case, we're using Flex and Bison to create it. Exactly right. So we're using Flex and Bison. We're using these little actions in Flex and Bison to create tokens and to create an AST node, to create AST nodes. And then we're going to, for our code generation step, we're going to use that to generate code. So somebody asked, do we need to download anything for Flex and Bison? The Vagrant provision script I gave you will have automatically installed Flex and Bison for you. So when I give you the code for this, you should just be able to, there's no homework that you have to do this, but I'll give you the code, just like the toy compiler last week. I'll give you the code. It's very similar to last time. And you can compile and run it if you like. So let me actually go into compiling and running this. So here's the kind of specification side. I'm giving you, so it's not like, I'll give you readings so you can look more into the concepts of Bison. There's readings at the end of these lecture notes. It's not a formal assignment because it's not graded, but I strongly recommend reading over the documentation of Bison because you're gonna have to fill out a Bison specification in order to do the first project for SimpleC. So this is at the end of the lecture. So there's readings for next week, the concepts of Bison and defining language semantics. So this is just the Bison manual. So I read it, please read it. It's part of the course. I think it'll be much easier to do the first project, which we'll give next week, if you read that. Okay, so just a little quick wrap up of what we just went over. The whole point here is that writing a compiler is long and tedious. And the whole goal of writing correct code is making the implementation match the specification. So if we can make writing code closer to writing specification, we can define a simpler domain-specific specification language that is easier to get right. And if we can automatically generate the implementation from that specification, then we'll have a better time writing correct code. And for our Tor compiler, the way we can do that is we can use Flex and Bison to automatically generate lexer.c and parser.c for us. And we're still going to handwrite the rest of the code. I sort of thought about, can we make a specification for that stuff? But this would require a little bit of new research that I did not have time or the will to get into for this course. Maybe in future courses. It'd be interesting to make this all specification based. Okay, and we looked at Flex and Bison. So read over those. Already online is a listing of the source code for the toy compiler. So it's very similar, except now we have lexer.c and parser.c. I've also separated out the AST creation functions because those were originally in parser.c. I just separated those out into a new compilation unit. They could also be in the Bison specification file. it doesn't matter. That's more of a choice. So you can, so somebody asked the question, is create statement list a function the user has to define? Yes. So Bison does not create AST nodes for you. Just like Flex, it just provides kind of pattern matching. And it allows you to write a snippet of code that does anything you want when you match that pattern. So when you read over the Bison specification next week, you'll see that they will, where is this? Okay, I did not, did I link to this? So they'll go over it when you read this. Where is RPCalc? Okay, I didn't provide an explicit link to it. But you'll see that you can put anything you want as the action to take when you parse. So the parser is just basically doing pattern matching. And the code inside of these braces, the action that you take can be anything you want. So in this case, you can just write an interpreter for a calculator. So this running example they have in the Bison specification, instead of creating AST nodes, they just compute the result. And so the return value of this set of kind of recursive parsing is going to be the result of the calculation. This is more of an interpreter, so I didn't want to show this as an example. I wanted to show the compiler part where we're generating assembly code. So Bison does not generate any values for you at all. It just provides you a way to specify the grammar as patterns and a way to specify the little snippet of C code you want to run when you see that pattern. And so in our case, we have to create the data structure, the AST data structure, the definition of it, and the functions to create the links for that AST data structure. But I'm going to give you the AST structures for SimpleC. We'll look at this next week. What your responsibilities for writing are and what I give you. So I'm going to give you all of the AST creation functions. You'll just have to fill out the Bison specification yourself next time. Okay. So I want to revisit a little bit of the system software stuff. I want to revisit some of the Makefile because I didn't really get to it very much in lecture 2. And it's sort of important to understand, to see how we can organize this compilation of our compiler. So now our compiler is a little bit more complicated. It's not just compiling a set of C files, linking them into our final program. Instead, we are now generating code first that we then have to compile and link into our compiler. So let me revisit Makefiles. Okay, any kind of lingering questions on the compiler stuff, the Bison and Flex? So I think I answered everything so far. Okay, so Makefiles are kind of like, I was watching some channel that where this guy does ports of homebrew software and does porting, and he was going over porting Doom to Xbox. It's this guy, Vintage Modern Gamer. It's actually a pretty nice channel if you're interested in emulation. And he was going over how he did a port of Doom to the Xbox, I think. And he was like, well, I had to take the Makefile and I had to like make that Makefile actually compile the thing. And he had a kind of a nice, he didn't go into the details of it. He was just like, well, from my point of view, a Makefile is basically a script that automates the build process. And I have to kind of tweak the things to get it right for the new platform I'm building for. And that's kind of a nice intuitive way to look at a Makefile. It's basically like a Flex is a specification of a Lexer. Make is a specification of a bash script that builds, that runs each of the commands you need to run in order to build your project. And so this whole class is about like language specification and how those get interpreted and compiled. So make is yet another specification file, and Makefiles, the syntax of a Makefile is you specify the target, the thing you want to generate. So this might be a .o file, this might be a .c file. This is the thing that you want to generate. These are the, somebody said they saw someone playing Doom on a pregnancy test. I don't know how that is even feasible. Okay. If you want to share the YouTube video for that, that would be interesting. There's only 2 lines. Okay. I have no idea how that's supposed to work. Oh, they replaced the screen. Oh, so the pregnancy test had some chip inside? I can't believe a pregnancy test had a chip inside. That's crazy. Well, if you replace a pregnancy test, you replace the screen and the processor and everything else, is it's still a pregnancy test? Okay. So a Makefile is so yeah, maybe they use the chip inside. That's pretty amazing. So so I'm not going to click on any links while I'm recording, so just in case. But I'll take a look at that later. That's very interesting. So yeah, so we have the target file. That's the thing you want to generate. So the GCC, when you compile, generates O files, .o files. So we put the .o file we want to generate here. And this recipe is the series of Unix commands, bash commands, or shell commands that you want to run in order to generate that target. So just like Flex and Bison, it's not automatically, it doesn't automatically build for you. It just provides a specification language for defining how to build it, defining what commands you want to run. It just provides a kind of template for doing that, rather than, a template for doing that. So why is it that we need to, write the commands ourselves just to build this target? Well, what Make does is it provides allows you to specify what other files your target depends on. So instead of a script which will always recompile every part of your program every time, instead, you can do incremental compilation with Makefiles. And so the automation it gives you is it automatically checks whether source files have been modified yet. And it'll only rerun the recipe for the target if any of these prerequisites has been modified. So let me show you a concrete example of this with our toy compiler. So here's our original toy compiler, more or less. And here was our Makefile. So, so in this Makefile, all it's saying is for any .o file, only rebuild it if the corresponding .c file has been modified. And this is the code for running the C compiler. So don't worry too much yet about these, money signs. These are just variables that hold the name of the C compiler. So if I run make, notice that for each C file, so this rule says that for each .c file, or I'm sorry, for each .o file, only rerun this recipe if the .c file has changed. So we can see that each of the, so only run if the C file has changed or the .o file doesn't exist yet. So this is how you create the .o file. If it doesn't exist yet, then we need to run the recipe. But now if I run make again, notice nothing happens. That's because Makefile is using these prerequisites to determine which files need to be rebuilt. So if I were just to remove lexer.o and rerun make, then it knows, because of this dependency specification, it knows that all the other .o files have been built already. And so here in here in program, this is saying that rebuild toy by running the C compiler, but only if these .o files are either not there or have changed. So because I removed lexer.o, this is going to say, well, I need to rebuild toy. But in order to rebuild toy depends on all of these object files, lexer.o, ast.o, etc. But it's basically a recursive dependency. There's kind of a tree structure here where it says that, okay, how do I build .o? Well, .o doesn't exist yet. Here's how I build it. Or the C file for lexer.o has changed, so I need to rebuild it. So for instance, I can set the, I can pretend like I modified lexer.c. So touch is just changing the timestamp. And again, lexer.c will be rebuilt. So if I modify any of these files, so I modify codegen and modify ast.c, when I rerun make, the make program is building a dependency tree to see which targets depend on which other targets in the language, or in the specification, the make specification. And it's only building those parts of the program where there are changes in the code. So to recap this one more time, the target is the thing we want to generate, a .o file. The recipe is how it gets built. The prerequisites allow you to define this hierarchy of dependencies between generated files so that make will only build those files where there are changes to code. Questions on this so far? I know there's a lot of details about the make syntax that I didn't cover. I provided a link to the documentation so you can look over it yourself. I'm going to give you all the make files, so you're not going to have to learn in detail how to write make files yourself. And even I have to look at the reference manual in order to like write them from scratch. I usually just copy something that exists already. So somebody's asking how moneysign.o is the same as the object as a prerequisite. So moneysign.o, I'll just show this file here. So I'm sorry, a %sign.o is a wild card. It's like star.o. It's saying for any .o file. And it's, you know, this is just the kind of details of the way make works. This moneysign.o is the corresponding match to the wild card here. I wouldn't worry about that too much. I would just read the manual on this. I'll give you the actual make file for this. Okay, so just understanding that this sets up this series of recursive dependencies on which files change. If we want to have generated files, so let me show a little, so if we look at this, if we think about this as like a tree of dependencies where in order to compile lexer.c, we first need to call flex to generate lexer.c. And in order to compile parser.c, we need to call bison to generate parser.c. We can use a makefile to help us organize the dependencies between these generated files. So rather than having to write a bash file that like, okay, well, let me make sure I run bison first, then run the compiler, and have to always rerun this generation every time I recompile my whole compiler, we can just define new recipes, new rules to generate the generate the parser. So here, this is saying, in order to generate parser.tab.c, so parser.tab is table, this is the bison naming convention. So in order to generate parser.c effectively, this is how I generate it. I run bison. And we need to, and it depends on parser.y. So if parser.y changes, we want to rerun this rule. And okay, so this is like, just like recursion, I want to just think about how I generate parser.c. And parser.o is handled by this rule. So in order to generate parser.o, I run this command, the C compiler, and I only want to recreate it if parser.c changes. So if parser.c changes, I want to rerun this rule. For parser.tab.c, there happens to be another rule that it depends on. So parser.tab.c will only be rebuilt if parser.y changes. Is that sort of clear? So I don't want to spend too much time on make. It's a pretty esoteric thing. But this notion of separate compilation and incremental compilation, where you only have to recompile part of your project, this was kind of popularized by Make. And this kind of set of recursive dependencies you'll see it in really any build system. So yeah, you'll see this in any build system. Ant or Gradle, they all have this notion of dependencies between makes. Okay, great. Yeah, so in lab, Josh will go into more detail about these make files and about separate compilation if you have questions, so about how this works. So yeah, so go to labs. So Josh, I think I'm telling him now, actually, so we didn't agree on this yet, but I think Josh, hopefully if you agree, you can show like the header files and how these work together, how separate compilation works together. I didn't cover this in so much detail in lecture 2 like I wanted to, I didn't have time to get to it, but Josh will cover this as well, you know, why include files are there. We talked about it a little bit, you know, declarations versus definitions. But yeah, so attend lab today, learn more detail about this. And in the last little bit of the class today, I want to introduce SimpleC. So any kind of overall questions about the toy compiler, compilers, Flex and Bison, anything kind of conceptually. So go to labs. Josh will go into more detail about the Bison format and how this stuff works. The compiler version of the toy compiler. But are there any kind of conceptual questions about compilers, about the toy compiler, anything, you know, compiler something? The Bison file gets compiled by the Bison tool. We get from parser.y to parser. So we get so it goes from parser. So we have parser.y. The Bison tool generates parser.tab.c, and then the C compiler generates compiles parser.tab.c into machine code. So the Bison file or the Yak file or the Bison specification is processed by the Bison tool. All right, let's look at the language we're going to be implementing together in this class, and it's called SimpleC. It's a little thing of my own invention. So the original iterations of this course used a very old Pascal-like language developed by Nicholas Wirth for teaching programming languages. Particularly because this is system software and I really want to go to the back-end low level and the details about C, because this is system software. This is, I mean, an engineering school. And at least until now, C is your starting language. I thought it'd be really instructive to learn not only how the C language works, and also learn how the system software works at the back end to make C runnable, to make the compiled versions of C runnable, and how libraries work, how linking works, how the programming environment actually works at the low level. I wanted to try to include enough details about C to compile real code that you can link with the C library. So my goal is to have you write a compiler that will actually integrate into the Unix environment, where you can call printf, you can call malloc, you can actually call the C standard libraries, but also make it simple enough that you can implement in a single semester course. So I hope I got the balance right. The language is not very small, but it does remove a lot of the complexities of C. We'll see how this goes. We'll see how this goes. We'll see how it goes. Okay, so here's an example of SimpleC. Now, you'll probably notice it looks very much like C, but there's probably some very strange syntax here that is completely different. So this is something that I kind of invented, took it from some of the type theory work to make, just to make the types more explicit. Okay, so some people are already saying they like it. So Josh, the TA, really liked this a lot. So I really took this from languages like Haskell or really the kind of type theory world, where you can be very explicit about how you write C. So I kind of invented SimpleC. I mean, it's not anything very deep. I mean, it's basically a subset of C where the type definitions look more like formal type theory stuff. So there's nothing, I mean, there's nothing notable here. This is more like it's for teaching. And so, you know, in my research work, I have a project where I do a lot of processing of C. So one of my research projects is to take the C language and deal with the build system and the preprocessor, which are actually not part of the C language, but transform them so that semantically the behavior of the build system is encoded in C. And it's an enormous pain to go through the syntax of C. And so I was revisiting in detail the nitty-gritty of the syntax and semantics of C, and I realized that particularly for declarations, we could make it much more explicit how the types are being defined. And so I just took the kind of type constructors that are used in type theory and program analysis and just made a very simple syntax for them. In fact, the way type theoretic work works is they have a grammar for the type specification. But okay, we'll get into that when we get into the syntax of the language. So okay, so declarations work very much the same way. You cannot initialize variables in the declaration. This is convenient for writing C, but it's a pain to compile. Okay, so the expressions and assignments and declarations all look very similar. Everything ends with a semicolon. You have the normal equal sign like in C, a single equal sign like in C. You have characters in the same way you have in C. You have dereferences. So I'm assuming that you guys have a pretty decent understanding of C, pointers and references. So you can do the same thing in SimpleC. So there are some restrictions that make compilation easier. For one thing, main is part of the language. Returns can only happen at the end of functions. You can't write a function without having a return. Expressions are very similar. So you can dereference variables with a star. You have all the classic operators. You can do typecasting. Functions are quite different though. So here, kind of like in old style C, K&R syntax C, you define the name and parameters of the function independently of the type. So this is the name of the function and the name of the parameters. And the type is specified independently using this colon syntax, which was very popular in functional languages like ML and Haskell. But other than that, other than this type definition, and this kind of declaration is similar in C where the type comes first. Other than that, the language is very much like a subset of C. Yeah, so somebody asked, are there no void functions? So void functions were not originally in C. And in fact, at the backend level, in the backend, all functions have a return value. According to the ABI, the application binary interface, the function call interface at the binary level, all functions actually have return values. Well, I wonder if the ABI was actually improved for having void. But anyway, void, yeah. So you don't have to have void functions. You could just ignore the return value and then you have a void function. So we don't have void functions in this language. Just I wanted to simplify the number of types we have. Okay, so the language constructs are just like in C. We have expressions separated from statements. This is something that functional languages don't do. Everything is an expression. But we still have this design choice of C where expressions and statements are separate. We have declarations, just like in C, where you tell the compiler, here's a new symbol, here's its type. And we have function definitions. Definitions and declarations are something that get kind of blurred in C, which is, I think, part of the reason why header files can be so confusing. Like, why do you need to have header files? Declarations are for the compiler to know about symbols, and definitions or assignments are something that actually have computational meaning that actually get translated to assembly. Okay, so expressions, I just took a subset of C. So Josh helpfully found a C grammar online, which is from like 30 years ago. And I just took it and basically stripped down the grammar. So we have all of our arithmetic operations. We have pointer, reference, and dereference, ampersand for reference, star for dereference. And then of course, as I hope you all know by now, arrays are just pointers in C. It's just syntactic sugar for a pointer, more or less. We have the relational operators and we have Boolean operators. So just like in C. So if you know C. Yeah, so I'll get to the functions in a second. Statements, also a subset of C. We only have 3 statements, if and while. Assignments are statements in C, in SimpleC. In C, they're actually expressions. I thought I had a example of this. Well, yeah, so I didn't put it in the slide, I put it in the notes, but yeah, so in C, you can do stuff like this syntactically because assignments are actually expressions. Let's not get into, I don't want to get into too much about, like, they're called L values, but let's not get into too much in detail on that. To simplify it, I just made assignments statements. Declarations, it's basically just like C, except we have a much smaller number of types. The syntax is different to make it explicit how we're constructing types. There are 2 main kinds of types. We have primitive types. There's different terminology for this in the literature. So I'm using, I think this might be C++ terminology. I don't really know. But in formal type theory, there's this notion of like primitive types versus type constructors. And so type constructors create things that are also called compound types. So primitive types, int and char, these are things that are like scalar values that represent a single value one at a time. Compound type represent type structures, like structs, arrays, and something that might be unfamiliar outside of type theory, unfamiliar when you're learning about C, is that a function is a kind of compound type. So it makes sense that pointers, arrays, and structs are compound types, because you're saying, well, okay, we have an array of ints, and so semantically it defines a contiguous sequence of memory that contains values of all values of that type. And a pointer is a different kind of value that stores a memory address, but the memory address holds a value of the type that you define the pointer to be, so pointer of int. But functions in C are not really conceived of as a function type, at least not like syntactically. So let me go over some examples of this before I go into functions. Okay, so declarations work the same way for primitives. For pointer types, instead of using that annoying star syntax, we just explicitly construct the type itself by using this bracket syntax. So I kind of stole this from Java generics or C++ templates. So this is like saying a pointer of ints. This is saying an array of a fixed size 5 to ints. So for arrays in this language, you always have to specify the size, kind of like stack allocated arrays in C. You have to give the size. Otherwise you're basically just defining a pointer. And if we want to do, say, a double pointer, you can, these type constructors are recursive. So here we can say a pointer to a pointer of characters. And so so does anybody know in C, sort of semantically, what does it mean to have a pointer of pointer to characters? So this is something that main takes in, argv is a pointer to characters. Good, yeah, so somebody said this, an array of strings, so very good. So semantically, we use this as an array of strings in C. Okay, so we're at 1250, so just a minute or 2 more. So function definitions, we have a very new syntax to this, but we make the type of functions explicit. We make a specific syntax for constructing the type of functions. And as somebody asked before, this arrow here, is this the return type? Yes, exactly. So the pattern of, this is actually a little wrong. So the pattern of a function type. So yes, somebody asked, is this like Haskell? Exactly right. So the pattern of specifying types in SimpleC is you specify, so this is the pattern. So this is the param types, and then return type. So this is kind of the grammar for it. In parentheses, we have a tuple. We have a tuple is a list, a fixed size list of types. And so in this case, it's a function that takes two parameters, each of which is a type, and its return type is an integer. So arrow is used to construct the function type. So in SimpleC, there's actually a grammar for defining function types, just like in Haskell. Of course, when we actually go to implement the language, I'm not gonna make you have functions as values, but you certainly could extend SimpleC to be like Haskell and have be a functional language. But I did this just to make it a little more explicit, the typing more explicit in the language. So when we do our type checking, it'll be, I think, a little easier to collect the type information from the input language. Also for function definitions, syntactically, SimpleC enforces having a return statement only at the end. In C, a return statement can appear anywhere. But this makes compilation annoying because you really only want to, it's much easier to write the compiler if you only return once at the end. And so this also means no void function. So you always have to have a return function at the end. So here's a definition example. Here we just define the names of our function. We use colon to separate the type. And then here is our function type constructor. And here's our return statement. So if we have a longer example, the return statement is always at the end. Here's a more complicated example where we have this increment array. It takes 3 parameters of these names. Oh, I forgot the colon here, whoops. And then our function type is a little bit more complicated because the first parameter is a pointer to integers and then 2 other integers. And our function actually returns a pointer to an integer. So all that kind of annoying syntax in C where you have to get the percent signs or the star signs right and the parentheses right is that's all kind of gone in SimpleC. Okay, so I think that's enough for today. So I actually posted the syntax and semantics of SimpleC if you want to take a look at it. If Josh has time, you can ask him to go over that in lab. Otherwise, I'm going to go over this next time when we go over project 1. So make sure you go over these readings. Yeah, look at the documentation. Remember, the toy compiler is due next week as well. So remember to finish that up. Look at the readings for next week. So you'll be able to wrap your head around Bison. We are definitely going over SimpleC again. So when I wasn't sure if we were going to get to it today in detail, but we're going to go over SimpleC. We're going to go over the Flex and Bison specification of SimpleC because for your first project, you're going to be filling out a Bison specification that I'll give you, and you're going to fill it out to call the AST creation functions. So we'll go over that in more detail next week. For online manuals, go over these. For the ones that say readings for next week, there's no Flex here. It's just Bison stuff. These will be essential for doing project 1. So I would make sure you really understand and grok these definitions, these manuals for how to use Bison. And then take a look at the toy compiler and the handwritten compiler you wrote to see the parallels, to see what's really going on when you write these semantic actions. All right, everybody, have a good weekend. I'll stick around here for a couple minutes to answer questions, and then I'll move over to gather for office hours at 1. So sorry for going over a little bit, everyone, but everyone have a good weekend, and I'll see you next week. So someone asked, anything we should work on other than the toy compiler? So nothing implementation-wise. You can certainly, so I sort of mentioned this offhand, but you can look at the Bison and Flex version of the toy compiler in the lecture notes. So I've given you the source code for that. And you could certainly, if you want to explore a simple version of Bison and Flex, you could just try compiling and running that and playing with that. Definitely do the readings. Oh, I forgot to mention the language design talk. Well, it's in the lecture notes. And if whoever rewatches this will see this. It's just, this is kind of an aside. This is a very nice talk that I referenced. Somebody asked a question during the break. But yeah, definitely do the readings for next week. But other than that, there's nothing for next week besides studying this stuff up. Okay, other questions before I move over to office hours? All right, everybody, have a good one. See you in office hours.